Hello, welcome to today's session of chemistry. In today's session, we'll be talking about polymers. Polymers are one of those really interesting, useful, and very commonly seen and available molecules in daily life. We see polymers on a day-to-day basis. We consume polymers in a day-to-day basis. And a lot of times we are actually made up of macromolecules that are polymers. Okay, something like DNA or proteins that are part of us. But we also see things like PVC pipes, the Teflon coated pans, right? The nylon fibers, and also our organic light emitting diode based screen on our laptops and televisions. These are all polymers. So before getting into the details of how polymerization process works, let's briefly talk about the types of polymers. And these polymers can be classified into mainly four categories, okay, based on different reasoning. First, based on their origin, whether they are natural, semi-synthetic, or completely synthetic. They could also be classified on the basis of structure, whether the molecules on the polymer in the polymers are all linear, or they are branched, or if the linear molecules are sort of cross-linked with certain units. Okay, that's based on the structure of the units within the polymers. The polymers could also be classified on the basis of how strong the intermolecular force is, right? Something elastomers, which are viscous and very weak intermolecular force, all the way up to thermosetting polymers, very strong intermolecular force, hard polymers, okay? You could also classify polymers based on the way polymerization process works. Polymerization process is basically when you have monomers that combine or under certain condition of temperature, pressure, and catalyst to produce this giant network of molecules, which are polymers. And that process is called polymerization. And based on how that process works, you can classify polymers into different categories. For this class, I'll probably talk about all this in our future lectures, but for the purpose of this class, we'll be focusing on polymerization based on, or polymers based on the mode of polymerization, mainly additional and condensation polymers. Our focus would be addition polymers, which we'll go into detail on additional polymers, but I'll also briefly mention what condensation polymers are, okay? So let's go forward. Before getting into the polymers based on the mode of polymerization, let me give you a little bit of a little example of those different kind of polymers on the base of the origin, okay? We've seen natural polymers, something like cotton or rubber, right? That we get right out of the rubber tree. These are natural polymers, very organically available in nature. There are some purely synthetic polymers, which are synthesized with artificial chemical reaction, human-made chemical reaction, nylon, silicone, not silicon. There is a difference. Silicone, those are synthetic polymers, right? Plastic would be a synthetic polymer. PTFE, polytetrafluoroethylene, would be a synthetic polymer, right? Or you could also have a semi-synthetic polymer, where what you do is you take a natural polymer and then add certain molecule and then subject that natural polymer to a certain physical process or chemical process to get a polymer of certain property, desirable property that you are looking for, right? Those are semi-synthetic, something like a rayon. This is a synthetic polymer derived out of a natural cellulose. A vulcanized rubber, that's, you have a rubber and you do certain processing into the rubber, artificial processing, and you get this vulcanized rubber. These are examples of semi-synthetic polymers, okay? So polymers are cool. They are super useful. We use them, we consume them, and we are also part of them in certain way. So it's a very interesting topic, not difficult, but really something you can connect to, okay? So that was on the basis of source. Let's talk about polymers on the basis of how the polymerization reaction happens when synthesizing these polymers, okay? And this is of utmost importance to this class. This is what we're going to focus on. So on the basis of mode of polymerization, or the way the polymerization reaction happens, you can classify polymers into two groups. Addition polymers, the process would be called additional polymerization. This is also called chain polymerization because you are continuously increasing the chain. Or you could have condensation polymerization, which is also called step growth. There's one step growth at a time. Okay, and you can see the example of additional polymers, something like polyethylene, plastics, polyvinyl chloride, something like pipes, polypropylene, polyvinyl alcohol. These are all examples of additional polymers. You could also have condensation polymers, something you have seen around, nylon, right? The ropes and fabrics. You have seen polyester, very commonly used fabric, proteins and nucleic acid, biomacromolecules that are within us. These are condensation polymers. And one thing I want to talk about condensation polymers right here is when you are undergoing this condensation polymerization, by the name itself, whenever you are joining two molecules, there is usually an elimination of water molecule. That's why it's called condensation. Most of the time, water molecules, 99.99% of the time. Okay. Sometimes there is an acid molecule coming out, HCl, HBr, maybe, right? But most of the times it's water molecule that gets eliminated during the joining process of those two monomers. Okay. So condensation polymers, also called step growth. Addition polymers or additional polymerization process, also called chain polymer or chain polymerization. I want you to remember the examples: polyethylene, polyvinyl chloride, polypropylene, polyvinyl alcohol for additional polymers, and nylon, polyester, and proteins and nucleic acid for condensation polymers. Okay, so that's the different mode of polymerization. So for this class, again, you don't need to know the detailed mechanism of how additional polymerization reaction happens. But since these are terms you have already talked about, or we are familiar with in our previous studies of chemical reactions, so I'm gonna highlight these terms a little bit. You don't need this for exam purpose, okay? So additional polymerization reaction happens through initiation, propagation, and termination step, something that we talked about in free radical substitution reaction in alkanes, right? You need high pressure and temperature. Temperature could be mild depending on catalyst, but the pressure is most of the time really high. And you can imagine why you need high pressure, because what you are trying to do is basically merge and push all these monomers, small units, and get a giant molecule out of these small units, right? So in order to make these molecules come in contact, you definitely need to push them a lot. So that's basically where the pressure comes in. And also you need to increase the temperature to activate these molecules and get the reaction going, right? And you also need catalyst for reaction to happen. This could be organic catalyst, and a lot of time it could be metal catalyst. We don't need the details, but you can sort of research yourself the different kind of catalysts used for additional polymerization reaction, okay? So these are some of the requirements. And talking about mechanism, the additional polymerization goes through three different kind of mechanism. The free radical polymerization, in which the free radicals are formed. The cationic polymerization, in which the cations are formed, positively charged species. The anionic polymerization, in which anions are formed, the negatively charged species. Okay, that's the three different kind of mechanism that additional polymerization reaction goes through. You don't need the details of the mechanism for this class. So I'll just give you how free radical additional polymerization would occur. So talking about free radicals, we talked about free radicals in free radical substitution of alkanes, and even that reaction, the free radical substitution reaction in alkanes, occurred through three steps, right? We had an initiation step, we had a propagation step, we had a termination step. Similar process here. First, you'll have a molecule that's going to form a radical, free radical. In this case, it's a benzoyl peroxide, which is going to form a phenyl free radical. And once you have this phenyl free radical, that's going to come and react with your monomer unit. Usually, in case of additional polymerization, your monomer unit is an alkene, okay, a double bonded compound. That's your monomer. For example, in case of polyethylene, your monomer is ethylene, right? In case of polytetrafluoroethylene, your monomer is tetrafluoroethylene. In case of polyvinyl alcohol, your monomer is vinyl alcohol, which is also a double bonded compound. So that's you have unsaturated compound as your monomer source. So when your free radical comes and attacks your unsaturated monomer source, you get a new free radical. Now this new free radical and go back and attack your monomer. As a result, your chain would be extended. It keeps on going and makes this huge chain of carbon compounds or carbon fragments, okay? and still a free radical. So this is chain propagation step. Your chain is continuing to grow, right? And after a certain time, depends on the temperature situation, pressure situation, the catalyst, the chain that you grew earlier, the long chains, they sort of combine together and form a stable compound, right? That's where the termination happens, and that's your polymer. And the length of the polymer, like I said, depends on the length of the chain that it grew, and that in turn depends on the condition. You don't get same length chain at the end of the reaction. Your final reaction mixture could be a mix of a chain that contains maybe 100 monomers or 200 monomers, 300 monomers. So it depends on the situation, but usually you get a really long chain monomers and a long chain polymer, and you get your polymer compound. Okay, but like I said, your final reaction mixture, your final polymer, though we represent it with a certain, well, even here you can see, right, we write N, we don't write a certain number because that number is variable. And when somebody asks you what's the N for your particular reaction, you usually take the average. Okay, if it's like 100, 300, 500, 600, then you take 400 as your N. But like I said, that's very variable. Even for one reaction subjected under one particular condition, the N will change. Okay, it's not a constant number. Okay, so that's how a free radical polymerization addition reaction works. Initiation step, propagation step, termination step. Something we have also done in the past in free radical substitution of alkane. Now, like I said, there can also be cationic polymerization, in which the intermediates or the most recurring intermediate is the cation. So even here, it's an additional polymerization. So you start with unsaturated compound, right? In this case, it's styrene. You add your catalyst, which is a positively charged compound, because this is a cationic mechanism, right? It could be sulfuric acid, which contains H+, or it could be a cationic catalyst that has a positive charge, or something that is really lacking in electron. So you attack your monomer with that, or your monomer attacks that positively charged compound. As a result, you get a positively charged intermediate, right? You can think about the electron flowing here. As a result, you get a positive charge here. You can draw the arrow pushing mechanism here. You've already done this, how to attack a double bond on a electrophile, right? And again, now this can go back, this intermediate can go back and attack a new monomer, right? The original monomer. And you can continue to extend this length until you get like hundreds and hundreds of these monomers tied together. That's the chain propagation step. That's the chain initiation step. That's the chain propagation step. And in the chain termination step, basically you have to neutralize that positive charge. Okay, you do neutralize that through introduction of an anion, a counter anion, right? We don't need this for this class purpose, but you can always go and research how do you terminate a cationic polymerization reaction. Okay, there could be simple addition of a negative species on top, or there could be elimination. There are different ways. I don't want to go into the details, but if you are interested, you can always research on the termination step. So that's a cationic mechanism. You start with a cation, you propagate through the formation of a cationic intermediate, and then at the end you terminate with an anion or a negative species, which is not shown here. At the end you get a polymer. In this case, it's a polystyrene. Okay, so now let's talk about anionic polymerization. Of course, in anionic polymerization, you're going to have an ionic species, which is going to initiate the reaction. In this case, it's a butyl carb anion, and this species is called N-butyl lithium. Really important species in organic reaction, which has a carbon ionic fragment, right? An ionic fragment. So the carbon ionic fragment is going to go and attack the styrene compound that we talked about earlier, in which the styrene propagated through a cationic mechanism. In this case, it's going to go through an anionic mechanism. So this negative charge is going to go and attack this carbon. The pi electrons are going to go and move into this carbon. As a result, you have a anionic intermediate. Again, this anionic intermediate can go and attack here on this carbon, and you can continue to extend this chain. Okay, and after a while, you'll get a really long chain carbon compound, and that's the propagation step. And at the end, you can terminate this with the use of counter ion or through other mechanism. Okay, that's not important for this class, but again, you can go and research on different ways you can terminate an anionic polymerization reaction. Okay, so we talked about free radical polymerization process in addition polymerization reaction. We talked about cationic polymerization process, and now this is anionic polymerization process or mechanism. These are the three different routes that your additional polymerization reaction can take. You always have a monomer unit, which is a double bonded compound. Most of the time, it could also be triple bonded, but we'll talk about double bonded compound most of the time. You have an initiator that could be a free radical, cation, or anion. You go through an intermediate that could be a free radical intermediate, cationic intermediate, anionic intermediate, and at the end you have to terminate your chain, long chain, and then you get your polymer compound. Okay, so one example of polystyrene is in the synthesis of the styrofoam cups, which are so commonly used in our daily life. Styrofoam is a really useful material. So that's additional polymerization reaction. Okay, so like I said, we don't need the detailed mechanism here, but what we're going to do is we're going to try to set up these two reactions. Okay, the polymerization of ethylene into polyethylene, the plastic that we see, and the polymerization of tetrafluoroethylene into polytetrafluoroethylene, the non-sticky material that we see in our non-sticky pans. Okay, so these two. Okay, so what you need to do here is let's say for the polyethylene, so you start with your ethylene, right? So this is your ethylene right here, C2H4. The double bond unsaturation is a really important criteria for additional polymerization. The addition happens because you have an unsaturated compound. This pi bonds, super important, the delocalized electron. So what I would do is then I would sort of like do this, and I'd say n number of this, because we don't know what that n, it's a variable number, usually hundreds and hundreds. I'll draw an arrow. I'll say high pressure, of course high temp. We don't need to know how high it should be. The temperature could be mild depending on the catalyst, and also you need catalyst. So now what happens is all these double bonds, since you add a cation or anion or free radical on top, so all these double bonds get converted into single bonds. So you change the double bond into single bond, and you form that extra bond on the outside because you are linking molecules. The hydrogens will remain as they were to start with, and this number will now change. You are going to have n number of this monomer units, repetitive units, right? That's called your monomer. In this case it's ethylene, and that's your polymer. Now all those monomers have been tied together on a single chain polymer. Okay, so you remember that number n. It doesn't have to be a specific number. This number right here, remember to put your monomer on a parenthesis. Remember to put this high pressure, high temperature catalyst situation and conditions, and then you get your polymers, and make sure that n is down as a subscript here, and you converted all your double bonds into a single bond. That's how you set up a reaction. Now let's write polytetrafluoroethylene. The monomer, of course, is tetrafluoroethylene. So what we'll do is it's an ethylene derivative, so you still have a carbon-carbon double bond, 2 carbons. Instead of hydrogen, you have fluorine. Polytetra, or monomer is tetrafluoro, so there has to be 4 fluorine on ethylene. So again, write N outside, same, whatever you did earlier, high temperature, pressure, and catalyst. As a result, your polymer would basically be connection of all those monomers, right? The double bonds would break down into single bonds because you are doing addition reaction on the double bonds, and you write your N down here. These are two simplest examples of additional polymerization. You can have a little bit of a complicated monomer structure-wise, but one thing you'll find is all of those monomers are going to have that double bond, and the addition is going to happen on the double bond itself. So I want you to sort of practice few more examples, a little bit more complicated examples, okay? Now, when I say complicated, the mechanism, the process is same, the setting up is the same, it just looks different. It's not going to be as simple as like a ethylene or a tetrafluoroethylene, okay? So please do that. And if you just know how to set up a reaction, you should be fine for this class. Okay, cool. Now we are done with additional polymerization, and we also talked about a couple example of how to set up additional polymerization reaction. Let's talk about the second class briefly, the condensation polymerization. Okay, and some of the examples are nylon, polyester, proteins, and nucleic acid. You don't need this for your exam purpose, but I'll just provide you the information about it briefly. Okay, in case of condensation polymerization, what happens is you have two units, and these two units can be different. Most of the time they are different. You can see one unit has this OH group and the other unit has to have a H group, because in condensation polymerization the important thing is when these two units combine, the water molecule has to go out. So there has to be a H source and there has to be a OH source, right? And these two units could be different, like it is in most cases, like here, or it could be a same molecule. Think about amino acids. In amino acid, there is a NH2 unit and a carboxylic acid unit on the same molecule. Okay, so the two molecules do not have to be different. They can be identical. They can be the same molecule. But in most cases, the two molecules, the source of H and the source of OH are different. Okay, so these two molecules are going to combine. As a result, the water molecule is going to get eliminated. The condensation happens. You get a new bond formation. The carbon is bonded to nitrogen. And that's the condensation process, and that process continues over and over. As a result, at the end, you get this really huge molecules, long chain molecules. In this case, it's a nylon 6. Okay, that's how condensation polymerization happens. We don't need to know the detailed mechanism. If you are interested, you can always go and check it out. It's not super complicated. If you are comfortable with drawing the arrow pushing mechanism, should be pretty straightforward. Might be 2 or 3 steps, but it's not really complicated. But we are not going to talk about it in this class. Basically, let's summarize what we have learned so far. We started by talking about how polymers are really important in our daily lives, how useful they are. We use and we see them and apply them in daily life all the time. And we also have polymers within our body, the macromolecules, the biomacromolecules, right? We started with that relevance of polymers. And we classify the polymers in these 4 categories based on the origin of source: natural, synthetic, and semi-synthetic. We talked about the polymers based on the structure. It could be linear, could be branched, or the linear chain could be cross-linked with certain units called cross-linked polymers. We also briefly talked about, we didn't go into detail, but talked about polymers could also be classified on the basis of the strength of intermolecular force between the polymer units. If it's pretty weak, then the polymers, of course, would be viscous, pretty soft. Those are called elastomers. And you could also have really strong bonding between the polymer units, which will give you a thermosetting polymers. Okay, and they have different application. One thing you should definitely keep in mind is the reason. One important research process that goes on in the field of polymerization is you always are trying to come up with new material with really interesting and useful property. Okay, and in order to do that, you always have to tune this reaction, subject these reactions to different conditions of temperature, pressure, catalyst, addition of something, a new chemical from outside. What you are trying to do is basically producing a matter which has really interesting and useful properties. Okay, so that's why sometimes the elastomers, which have their own application, are produced, and sometimes you produce really strong, rigid polymers with their own interesting application. Okay, that's based on molecular force. You can also have polymers on the basis of the mechanistic side, right? How the polymerization reaction happens, mainly addition polymerization, or called chain polymers, chain growth polymer. You can also have condensation polymer, which is also called step growth polymers. And these two were the focus of our session. We mainly focus on additional polymers. We talked about the different mechanism the additional polymerization reaction could happen through, the free radical process, the cationic process, and an anionic process. We also talked about 2 particular examples of additional polymers, the polyethylene and the polytetrafluoroethylene. We talked about how to set up the reaction. And the other mode of polymerization is the condensation polymerization, where you produce condensation polymer. We took a particular example of nylon 6,6, where you have a H donating group and an OH donating group, and there is a new bond formed with the elimination of water molecule 99% of the time. Okay, so that's condensation polymer. So that's basically the recap of what we have done. I want you to be a little bit research oriented. I want you to go back to the topic and sort of research yourself. Go to YouTube and see videos of how polymers are made. Research on different polymers and see their application in daily life, and see why there is so much interest in the field of polymerization. Why do people spend so much time and effort and money on coming up with this, like, different polymers? See their application. This is a really interesting. It's a short unit. You'll probably get 1 or 2 questions, but really important unit in terms of how interesting and relevant it is. Okay, so yeah, thank you for listening. I hope you guys like polymers now and see why they are super important, and do a little bit more research onto it. I'll see you guys in the next class. You guys take care and stay safe. Bye.